Okay, next let's welcome Stephen Watson to the stage, who is a lecturer of building energy at Loughborough University with a master's degree in mechanical engineering from Durham and an MRes with LoLo again. And he's currently analysing, monitored and empirically modelled data in building energy demand.
Good afternoon, everyone. So I will try and focus on the methods and kind of define the problem during my PhD, find what we actually trying to find out. And then I will talk about some results. I can go through them relatively quickly and then finish with a few thoughts at the end. So defining the problem. So we want to decarbonise domestic heating. We want to reduce heat demand. That's a big thing to do as well. But as well as that, we want to move away from gas boilers and burning oil. So that's the context. And there's a few different ways being thrown around about how we can do this. We could keep burning something, but that's something to be something else, hydrogen or biogas, like that. We could have heat pumps that provide electricity to bring heat from outside the building to the building. We have other types of electric heating, maybe we would have storage heaters or some other sort of direct electric heating. Or we have district heating, which would be a way to use a range of different sources to bring heat to the building through networks of pipes under the ground. And at the time that I was working, there was lots of different people throwing out suggestions of how we should go about this. With all relatively respected organisations throwing out completely different suggestions of what future heating could be like. So there'd be mainly heat pumps, there'd be mainly district heating, is it could be neither of those, all sorts of ideas floating around. So maybe the question that I should be looking at is, are heat pumps a good idea? Because people were saying they're not a good idea at the time, saying it would create tremendous peaks in electricity demand. We just can't deal with that. So they're a bad idea. So that could be one question to think about. Or another question would be, okay, we've already decided that heat pumps are a good idea. So what are we going to do about them? We know that we're going to use more electricity. So how are we going to prepare the electricity system? So if it's the first question, then maybe we need to make a comparison with the other options that are available, try and figure out, kind of assess all of them and the pros and cons of all of them, and then say something about heat pumps. In the latter case, we already decided that heat pumps are the way forward, so we don't need to analyse these other options. But in this case, we're talking about sort of planning ahead, sort of 5, 10, 20 years ahead. So we need to not just look at the scenario of what's going to happen, let's say in 2050, but we also need to think about, lots of intermediate points, how this is going to evolve over time, so we can gradually adapt the electricity system to cope. So that's going to affect what we're going to do in the project. And you think about how much electricity the pumps using at the moment. So current installed pumps, we could have a look at them. But then maybe it'll be different in the future. So should we be thinking about things as they are now, or should we be thinking about things as they are in the future? They might be different in a range of ways. So if we're going to go for heat pumps, there'll be a lot more heat pumps, but maybe they'll start working a bit better. Maybe the installers will start to do a better job. Maybe the manufacturers will improve their designs of heat pumps. Maybe the way people change. Maybe the way people use it to begin with was just as had boiler before, and they just always carry on with what we did before. But as they get more familiar, they start doing different things. We're expecting changes in the climate, and we hope that there are going to be some changes in the building fabric as well. And actually, the starting point of the whole project was really this question here of people use heat pumps differently to other heating systems. And this came from Maria Len, who was on the advisory board, and she worked for EDF, and they have a lot of electricity in France, much more than here. And she was very surprised by seeing the large peaks in demand that we see with gas heating in the morning and evening, because they don't seem to see that in their analysis of French electricity data. So is it something to do with France, or to do with electric heating that seems to give us different patterns of use, or is it something to do with the way that they're analysing the data? So we've got all these different sort of questions floating around, and we need to sort of pin that down a bit more before we can then figure out how we're going to address this. The other thing, and Meg's probably going to be quite bored in the next minute or two, because I'm always going on about this. But what is this? What is the scale we're interested in? About individual buildings, or maybe the local area? Because in that case, we're thinking about maybe the local electricity system and the distribution network is that which needs changes made to it, new transformers, new cables into the street. Are we thinking about this from a national point of view? So can we generate some electricity nationally, or maybe regionally? So might interface in the electricity system at different points. And we went as far as national there, but is this applicable beyond UK, or are we only focusing on what happens in the UK? You know, when we publish papers, it would be nice that has something international to say rather than just being nationally focused. And what timescale are we interested in? We're talking about minute-day electricity demand, we're talking about annual, you know, something in between. And those two questions are kind of related to each other, partly because if you were looking at national electricity demand, you know, at a minute-day scale from all different buildings all at once, that's going to be an unmanageable amount of data, but also because what actually matters would be different spatial skills. You know, if you're talking about an individual building, you might actually need to know about it minute-day because you've got these very short spikes in demand from things happening in the building, whereas maybe if you're looking at a national level, that's no longer what you need. And I guess monthly and annual questions, you know, this is, I think, it's always a bit of a change of mindset, you know, that historically, we're thinking about energy demands, we're thinking about annual, because if you're burning gas, for example, then you just need to know, oh, we're burning 10,000 kilowatt hours a year of gas. Okay, that's fine, it doesn't matter when it happens in the year, that we just need that much gas. We're done. But if you're talking about electricity, renewable electricity, then the timing suddenly becomes extremely important. So maybe annual isn't particular. So thinking about all those sort of ways of defining the problem, I decided to look at national electricity demand, and that was partly. So I think that looking at a local level is also really worthwhile. I chose to focus on national, partly because the cost of generation of electricity is probably the biggest cost, rather than what is upgrading the network. So generation matters at the national level. I chose half hourly. That's partly driven by the data that I had available to me, also because the electricity market works on a half hourly level. And I wanted to look at, okay, what's happening now, but how we expect that to change in the future, how we take that into account. This isn't word for word what I had in the thesis, so I need to check that it was exactly what it said there. So how are we going to approach this? So one method would be thermal simulation. And that would give us this high temporal resolution that said 1 to 2.5 hourly. It's important. So we could do that. We would need to know quite a bit about the building fabric of buildings. And that, you know, we could definitely do that for individual buildings. If we're looking at the land planning thought, we'd have some architect to represent different categories of buildings, so that might be fine. We would need to know what people are doing at different times in different homes. We'd need that information. But the key point here is that diversity would be hard to represent. This is something that Robert Sanson pointed out in his thesis, and when I read that, I thought, oh yeah, that's exactly right. I mean, kind of maybe if you didn't follow what I'm thinking already, but just emphasise that yeah, he was addressing a somewhat similar question, and he started off actually doing some thermal simulation, but then realised once he'd done some, this is the challenge. So diversity is the fact that not everyone does things at the same time. This is a good thing because it means that, for example, electricity networks don't need to be sized big enough for everyone to do the same thing at the same time. Similarly, water pipes or all sorts of things, road networks. So peaks of demand don't perfectly coincide. So if you add up, if you get the maximum of everyone's electricity demand, and then you add it all up, so say that your max demand is 10 kilowatts and mine is 8 kilowatts, and you add that together, we get 18 kilowatts. In reality, if you combine the electricity demand from George and from me, max is going to 18 kilowatts, so we're not going to have that happening at the same time. And that the ratio of those two is the peak coincidence factor. So that's a number less than 1 because of the fact that we don't have our peaks in demand at the same time. We do things at different times at different houses. So peak's going to be less. How much less? What is this peak coincidence factor? And it depends on lots of things. You know, we can get values of this for existing electricity demand with things like kettles and cookers and so on. But the numbers that we have for that don't necessarily apply to so if you've got kettles, you know, that's pretty powerful. That's used for a very short time. So the peak coincidence factor is pretty low because the chances of you putting on your kettle at exactly the same moment as me are not that great. If you're talking something like heating that uses for quite a few hours, the peak coincidence factor is going to be a bit higher, how much higher. So this is the problem that if we're interested in national electricity demand or even electricity demand from a group of buildings, it's pretty tricky. unless you can see something like this peak diversity or peak coincidence factor. And it depends on these things. We don't really know, or didn't know at that point in time. So to do that, we would need accurate knowledge of these schedules by these various different homes, which I didn't have at the time. But maybe you could do this, and I think that would be an interesting thing to do. I didn't do that, but you could, I think. Maybe somebody can try. Maybe you can get a data set of lots of monitored temperature data from lots of homes and figure out when, what's the range of heating patterns, and on the basis of that, what is the peak coincidence factor, and how does it then affect the demand for heating and electricity if they're all from heat pumps. Maybe somebody here could do that, you know. So I didn't do that, and so I started thinking about more about monitor data, specifically from this trial of smart meters. So now there's things like Sarah, where you get access to smart meter data that didn't exist at the time, and also heat pump field trial data. And that shows us what's really happening in homes, which is good. So we're not just assuming that people do things at particular times. And it allows us to represent diversity in real homes, real homes. How does that fit together when you add them together? It's good for journalists for what happens right now, but it's kind of tricky for what happens in the future, because we don't have the flexibility to change lots of things and see if we're going to add insulation to these walls here. How is that going to change the demand? You could answer that question with thermal simulation, but it's going to be a bit more difficult here. But the main problem was that we had a lot of data from homes with gas boilers that were, as far as we can tell, representative of the housing stock. And then, but we sort of thought, well, maybe people use boilers differently to heat pumps. And then we've got a lot of data from homes with heat pumps, but we know for sure that these homes are not representative of the housing stock. These heat pump homes are either large rural homes with relatively well-off occupants, or they're social housing. About 1/3 private, large rural homes, 2/3 social housing. So that's not really representative of the housing stock. And this is the main puzzle: was how do we piece this together? How do we come up with some method that represents how people actually use heat pumps, but it always takes account of the fact that this isn't the right housing stock. There was lots of data cleaning to do. So we've got a relatively large data set. I hadn't done something like this before. So there were 4 different electricity suppliers involved in the smart meter trial, and I have the feeling that there was some condition that they had to make the data available afterwards, but nobody put any effort into making it usable because they were just forced to do it. That's the feeling that I get, because it was all just bumped into one file of 4 different suppliers in a random order. I guess like there was a few data points to start from 1 year, and there's a few data points over here from some other year. Who knows what's going on? A lot of work for me to try and make sense of that and identify the problems and sort them out. As far as I'm aware, nobody else has done that. So other people that have looked at ERBE data have just taken the electricity data from one supplier, or separate data set from just one electricity supplier, and maybe they were able to deal with that. As far as I'm aware, other people have got this data and thought, oh, I can't be bothered with that. I'm not doing it. Maybe they're sensible people. So there's lots and lots of work going round and round. You think you solved it, and then you find something else going on. Think, is it real? Is it not? Am I biasing the data set if I take this out? What does this actually mean? The heat pump data, so it's a bit smaller, but I've measured higher resolution. We've got a bit more information about the buildings. But there are also other lots of that data set, particularly UCL, had a hard time with that because they were responsible for writing the report on that data, and they stopped up for the data after it all been collected and said, oh, people will tell us what it all means. But they had no involvement in collecting data. So there were problems, but they couldn't go to the homes to identify what problems were. If you ever mention this to anyone in the econ industry, they'll have a great big rant about how it was a load of rubbish and people at UCL don't know what what they're doing, and they didn't know the first thing about anything. Yeah, I mean, if you're like, if there's an awkward silence or something, you can just say that, and then they'll just keep talking at you for ages. Yeah, so I did advise I could try and identify problems and do kind of data. I mean, you hope that once you've done all that, you've identified the problems and removed the homes with those issues. Maybe you can't know for sure that you achieved that. That's what you're trying to do. Yeah, things like maybe the temperature sensors being strapped onto the outside of the pipe rather than inserted, so they're actually in the flow of the water. The heat meters being calibrated for pure water, whether it's actually mixture of antifreeze and water capacity. Something going a bit weird with the heat meters, the flow was sort of gradually declining over time, suggesting that something not quite right there. It's measuring heat in general is a bit more tricky than measuring electricity. You've got to measure flow rate and two temperatures correctly. And if any of those three things are wrong, you're reading wrong. Whereas electricity is that easier to measure. So I was going with monitor data and after thermal simulation, the reason I described. I started out by in the relationship of natural temperature and daily heat demand from smart meter data. And then I looked at the patterns of heating in the gas data and in the heat pump data to understand how we're using gas boilers and heat pumps. Is that different? It kind of was one of our starting questions. And then look at how does that affect this relationship between daily outdoor temperature and daily heat demand. Is it different for people that use heating all day versus people that use it morning and evening? So that there's a stage sort of slightly skipped over after that, which is then to look at how we use the heat pumps and how does that then convert from daily into half-hourly demand. I'll explain that later. And then, so that gives us heat demand. I want to talk about electricity demand, so we can how well the heat pump performing. So again, using the RHP data. So this was the daily heat data, daily electricity data. I tried to steer away from using the heat data as I could, because we knew that was where the biggest issue was, but inevitably you have to use it somewhere to get this relationship between heat output and electricity input. Look at different weather data, so analyze to look at what might happen in the future. And then hopefully heat pumps will start performing better. So we could look at just a subgroup of the best performing heat pumps from the sample, see how that looks. And indeed, there has been another study of heat pumps since then, and there hasn't been some improvement. And then look at different subgroups of just almost with a particular heating pattern to see whether if heating patterns do change in the future, how much of a difference is that actually going to make. So it's 4 results chapters. I'll try and how are we doing for time?
5 minutes.
Right, good. I'll talk about these more quickly and then I'll say a bit more at the end. So this is the first bit. Look at the current situation. That's what I was talking about daily heat demand. We've got this broken stick shape. That's what you'd expect because this bit down here is when most people have stopped using their space heating. So it's not as much related to temperature, whereas that bit on the left is when people are using space heating and that's strongly related to outdoor temperature. This is one of the sort of key points, which is that the way that's spread out over the day is different at different outdoor air temperatures. So when so you're all in the same area underneath. At the warmer temperatures, you've got quite a big spike in the morning and the evening, the sort of flat a bit in the middle of the day. At the colder temperatures, it's actually more flat in the middle of the day. So that suggests that perhaps when it gets colder, there's more people using their heating through the middle of the day. Whether that's that maybe they've got a set point that it doesn't normally fall down through the middle of the day, or they're manually fitting around to a thermostat, who knows? But that's what's happening, and that does fit in with what people have said anecdotally in the past. So you can use that to then get this half-hourly heat demand. You can split that into space and hot water. Comparing to Robert Sampson's, this is quite interesting. He looked at this before, it's a similar method of a much smaller data set, including only relatively mild weather and not accounting for this way this shape changes. And so a graph based on his work was floating around at the time, and what he found was these tremendous spikes in heat demand and very steep gradients. So around that's then the gradient you see goes shooting up very steeply. That's what we're using that to say heat pumps are silly because how can we possibly design an electricity system that can cope with these tremendous swings in demand and huge peaks? But I found that actually it was much less severe than that. Okay, there are big peaks of demand. This is a big challenge for sure, but it's not as bad as that. And that seems to be of interest to quite a lot of people. There's been another paper by some other people using a completely different method, and their findings, more recently, their findings were fairly close to coronavirus, so that was quite nice to see. These are the heating patterns found using clustering. I won't take too much about clustering now, you can ask me about it later if you're interested. But we find the same heating patterns for boilers and heat pumps, but in very different proportions. So most people are running it continuously, which is kind of what you'd expect it to do. But nevertheless, there's still only 63%, I think. So it's still about, a third of people are not doing that, which is kind of interesting. Is that going to change over time? But I can get more heat pumps and we'll have to run them through the night. Or I'd actually like to be a bit cooler downtime, I don't know. Because we've done that, we had the opportunity to look if there's any other factors affecting that. We can then look at the effect of that on the daily heat demand. It's like what I showed you earlier, but just for the subgroups of sort of different particular heating patterns. So you can see then that if people switch from one set of heating patterns for boilers to another set of heating patterns for heat pumps, you can see how that's going to change their daily heat demand. Over the course of the year, that's going to give about 8% more heat demand when you switch from a boiler because you're starting to heat more hours per day, which fits in with previous estimates. The same thing for heat pumps, but now it's a slightly different shape because there's a lot more people using through the night than they were with boilers. And so you can do that same kind of method as I did before with the heat pumps. And you can see the peak demand with the same wider data. That peak demand's a bit lower. Heat pumps, we both use them through the night, it's not such big spikes in the morning and the evening. 157 and 170. But the ramp rate is much less, the gradient is much less, so there's not that sudden everyone turning the heating on in the morning and it's going shooting up. So that's been interesting as well. So it's not such a severe challenge for the electricity system to cope with. And then we look at that for space heating and hot water, looking at the coldest day of the year. So the solid line is the one I showed you before for boilers. And then these the dashed black line is for the heat pumps. So you can see that heat pumps are being used differently to boilers. There's a lot more people using it through the night, so there's a lot more demand in the night. But any of them are much less than what was previously been suggested. Reasonable how the heat pumps are performing. This is regular sort of heat pumps. This is the bit on the left. What you expect is it gets older, the heat pump performs less well. It's also going down a bit on the right. There's probably heat pumps not really designed to operate at that temperatures. But it doesn't really matter too much because the heat demand there is pretty low anyway. So in fact, heat pump performing not that well isn't such a worry. There's a lot more scatter for ground source heat pumps. There's not that directly affected by the temperature. Maybe you could say that this is the wrong approach. Just look at that, it looks a bit questionable. And then we take subgroups of the best performing heat pumps for ground source and air source. So you can put it all together. I call this base case. It's kind of like the worst case, really. Assuming that there's no improvement in anything since now everything just stays as it is now, and it's a really, really cold year. This is what we get. We get so 76 gigawatts of thing the electricity demand. If everyone has a heat pump, nothing else has improved whatsoever since the current situation. Current peak electricity demand is about 60 gigawatts, so you're still talking about more than doubling the electricity demand. So that's what it looks like if you add on to existing electricity demand. But look for the flexibility, won't say too much about that. But then looks at what all these different things change, climate change, from frequency buildings, and frequency performance. What does that look like? You can see there some effects that might have, and then we went for what we thought was the best estimate of some reasonable assumptions. Other people would disagree. They can go to previous graphs to see what they think it would be. To see, okay, what might it be like? And this is the those are the results we found. So okay, it's still a big new electricity demand, but it's not something completely unrealistic. So this is what I want to say a bit more about, so trying to get through the results quite quickly. So we don't really know if you usually the building there's a change in heating patterns. Do they think, oh, this is great, I'll need to put heating on for 2 hours a day? Or do they think, well, there's no point in turning heating off because it is really inefficient anyway, so we've got to sleep on 24 hours a day. I don't know. Has the data cleaning worked? We hope that we've identified problematic data without biasing the data set by removing good data. Look at the very good heat pump, particularly the ground source, that's quite a small sample size. Is that realistic or not? You saw there's a lot more scatter in the ground source heat pump performance anyway. Is that the right approach to it? The metadata for the gas data was quite limited. There's 2 new data sets which you can use now if you're doing the same project now. You've got several smart meter data. Okay, it is within the secure lab thing, which is a bit tricky, but you can do something with that. And the electrification peak is kind of like a follow-on study of performance. Now, What sort of forms it better, the data is better quality, you might get some interesting findings. And maybe somebody could choose to do service variation, maybe there would be some value in doing that, but taking into account the variation to get real homes. The last thing I want to say is that what I presented to you today seemed quite, well, I hope it seemed quite logical. And, you know, we sat down and we thought out, okay, what's the problem here? This is the problem. Okay, here are the ways we're going to tackle it. Right, we're going to pick this one, but this one's the best. But actually, what really happens is much more like this ball of noodles, because everything is connected to everything else. It's all sort of tangled together, and you know, you tried one thing, and then you got so far with that, and then you realised it's actually a bad idea, and then you did something else, and then you thought you solved it, and then you realised there's actually problems with data cleaning, and there were some other issues with data. So you have to go back and start and be part of all of it, and then you have to try and write it down for other people to understand. And what you need to do is don't write that down, because nobody will understand. You need to write it down as if you knew what you were doing from the start. Write it down in a really clear and logical step. And I find it difficult because things to be obviously connected. You know, you think this is part of the method, or is this actually a result? And you know, is this data cleaning, or what is this? So yeah, you have to. That's what really happens, but you have to write down in a very logical step-by-step way if you really knew what you were doing. That was the end.
So we have time for 2 questions, and because of the time and delays we've had, we're going to have a short break as well, if that's okay with everybody. And there's tea, coffee, juices and biscuits, and then we'll begin Laurel's presentation at, let's say 3:50. Okay, any questions?
Yeah, so first of all, I think that's a very interesting research, very exciting, you know. Because you talk, you're interested in estimating heating demand of a bunch of buildings, building clusters, a huge number of buildings. I just was wondering, have you ever considered using gray box for these purposes?
I didn't in this project, but I agree that could also be a very viable approach. Yeah.
The Robert Sanson graph, I remember this, it's fascinating, because a lot of people were using that, I think, it's all like, you know, heat pumps will cause all these spikes, but if I remember correctly, that was kind of a really simple calculation that it's almost like writing a piece of paper, switch out a few numbers. Is that right? Is that a case of something done relatively simply, taking on big significance trouble?
Yes, I think it was. Robert Sanson said to me, "Get £1 for every time somebody uses graph and you're really rich." Yes, I mean, so what he did was he used some data from a trial of micro CHP units. There were 52 micro CHP units, but alongside that, 19 normal gas boilers monitored. So sample size of 19 boilers. And so if you're trying to represent diversity, you know, once you get to a certain number of whatever it is you're talking about, boilers or water use or whatever it is, at some point it's going to get flattened out and it's fully diversified, and adding more numbers won't make any difference. In this case, that actually happens probably around between 1 and 400, something like that, 1 and 400 homes. So the fact that I have 6,000 homes isn't actually adding to representing diversity. But you don't know that until you've gone way beyond that point. Then you can say, well, this is approaching being horizontal. So we had 19 gas boilers, and they were monitored, I think, between something like February and June of 1 year. And so he took away that variable reports per day from all those days averaged together, and normalized that. And then, as I did, find a relationship with outdoor temperature, you get daily identity profile from weather parallelism. So what I was doing was sort of building on that, improving it. Bigger sample size, improve cold weather, and improve the fact that actually it's different. The shape is different in the cold weather than the mild weather.
There's something with a sample size of 19 that's almost sort of trying to be good with policy.
Yeah. And it wasn't really, his thesis went on to do a lot of other stuff after that. It wasn't like the main finding of the thesis or anything.
Do we have time for one more question?
I'll ask the second master.
Sure.
Yeah.
Stefan, because you want to estimate the real power consumption of heat pumps, did you have difficulties to model the real heat pumps? Because, for example, I'm using Design Builder, and the Design Builder has some components for modeling heat pumps. But if I want to, for example, model a real given heat pump in Design Builder, I have to use engineering data books of heat pump unit, and there's a big spreadsheet that I should input maybe tens of numbers, to like, for example, power consumption of heat pumps under different outdoor temperature, indoor temperature, blah, blah, blah. So basically, it's a very frustrating task, to model the existing real pump exactly in Design Builder. Did you have such a challenge?
Yeah, I was interested in, well, at least initially in how do heat pumps actually work out there in the real world in people's homes. And so I got the daily COP of all the heat pumps in the sample for a given day, and I plotted that against outdoor temperature for that day. And this is what I ended up with, and I fitted this holistic regression for that. So I didn't get into what's actually going on inside the heat pump, how much of that is for the compressor, how much of that is for other components in the heat pump, fans, pumps, and distributors, whatever else is in there. It is, I guess, a question of should we be looking at how heat pumps actually perform in real homes right now, or how well could heat pumps perform if they were set up well and running properly. And I think that's that's what the heat pump industry board are quite getting angry about, because they know that heat pumps can perform much better than that. But what you're trying to find out, if you're trying to find out how well can heat pumps perform in this home, that's one question. But if you want to say what's actually happening out there in the wild, that's what's happening now. With the new data, there has been improvements in performance instead, which you can see. And though this itself was an improvement on the previous heat pump field trial, which was 2008, 2010, it's smaller, but was an improvement in this trial. So it did move in the right direction. But main problems with not being installed very well. I think the manufacturers themselves have also improved their control algorithms, so that they're not cycling on and off necessarily.